Hi, good afternoon and welcome. And thank you for tuning into this webinar. I'm sure it's a beautiful summer day outside. My name is Satish Joshi, and I'm a professor in the Department of Ag, Food and Resource Economics at Michigan State University. And I'm joined by Scott Loveridge and Brent Ross, who are also faculty at MSU in the same department. And Scott is also the director of NCR CRD, which is hosting this webinar. Okay, so at the beginning, so although only three of us, that is me, Loveridge, and Ross, will be presenting today, talking today, we like to acknowledge the other participants in this research, the co-PIs, Subbu Kumarappan from Ohio State University, and Steve Yanni at Bay Mills Community College. And also all our graduate students whose work will be presenting, that's Hoang Lee, G.U. Lee, Guilherme Signorini, and Alex Smith, and Larry Jacks, all at MSU. Okay, and more importantly, this research that we are presenting was funded by a 3-year USDA NIFA grant. The number is there on the screen, and which was, the title of the project was Decision Support Systems for Regional Planning and Impact Assessment of Biorefineries. So we heartily thank USDA for the support. Okay, before we begin, quick administrative stuff. So we'll be presenting for about 30 to 35 minutes, and we'll follow it up with a question and answer session. You can send your questions through the chat box on the left hand side anytime, and we'll try to answer as we see, or we can always wait till the end and we can try to answer. And obviously what we are going to present is a very high level summary of this research project. We'll be very happy to share more detailed outputs, basically the journal articles, and we have 4 MS and PhD theses coming out of this research, so we'll be happy to share those theses. Okay, and so to begin, the motivation for the project, we all know about the RFS provisions, especially the cellulosic ethanol provisions of ESA, that is Energy Independence and Security Act of 2007. It mandated, it mandated the use of about 16 billion gallons of cellulosic ethanol by 2022. And most of us are aware that the only thing that we have done consistently is to fail to meet those annual targets, which have been revised downwards every year. Like, for example, the 2016 original target was 4.5 billion gallons, and just a couple of weeks back, EPA revised it down to 206 million gallons, which itself is pretty ambitious, given that we only produced about which is about 6 times what we produced in 2014. So the challenges are throughout the value chain, starting from feedstock production, supply chain establishment, conversion technology, scaling up, distribution. So in this webinar, we'll be talking about some of the decisions that the biorefinery managers are facing, and some decision support tools we have developed to address some of these decisions. Okay. So just to give the types of decisions that biorefinery managers have to take are, okay, where should I locate my biorefinery? And once you have a biorefinery, what is the optimal spatial and temporal mix of feedstock? What feedstock I order from where? I enter into contracts from where and when? And then, given that here is the mix of feedstocks, what's the optimal configuration of biomass supply chains? And how do I structure these biomass supply contracts? How do I ensure participation of small tribal minority farmers? And also, how does the land use and supply in the region evolve over time once we have one or two or more biorefineries, and what does it mean to my biorefinery? So those are the types of questions, and so in order to respond to these, the project had six components. So the first one was survey research aimed at assessing the acceptability of biorefineries, whether communities welcome biorefineries or they oppose biorefineries. Is it a NIMBY phenomena or not? And then a biomass harvest shed design tool to help the optimal mix of feedstocks, both spatially and temporally. A logistic decision support tool to help evaluate alternative feedstock configurations. We are specifically looking at what you call distributed pre-processing of biomass, which we call as regional biomass pre-processing centers, RBPCs. We'll talk about it more later in the webinar. And then we did a case study on the RBPC financial analysis in eastern upper peninsula of Michigan, where it's the Bay Mills Indian community area, and then contract design research, and then dynamic agent-based simulation modeling to look at the evolution of the harvest shed over time. So Scott Loveridge will be talking about the biorefinery acceptability, the first component, and then I'll briefly touch on the next three components, and then Brent Ross will be talking about the last two components. So Scott?
Okay, thanks very much. Yeah, so to explore further the acceptability of having a biorefinery in one's community, we relied on a telephone survey of 1,000 Michigan households, and we were looking at, whether they would want a biorefinery in their community, and then reasons to either want or not want that biorefinery. And the bottom line on this is that very quickly that 65% supported having a new biorefinery in their community, so pretty strong majority supported it. There were 27% who were opposed to that notion, and then 8% were undecided about it. And so then we explored that a bit further, using the data that came from the survey. We were able to identify the respondents' county and then use county level data to do a statistical model that would predict the acceptability of the biorefinery in all of the 83 Michigan counties. And so that's what this looks like, the output of that model. So this is a modeling exercise, so it's a predicted probability of support of the biorefinery in a community based on that community's characteristics and the characteristics of the people who responded to the survey. So the red counties are the places where the most people would be predicted to be supportive of that new facility coming in. So in those places, it was more than 90%, predicted that more than 90% would agree to having the biorefinery come into their community. And then the pink is slightly lower, that's between 80 and 90%. The white counties are 70 to 80% favorability, and then the light blue counties are 60 to 70%. And then the dark blue counties are still mostly majority supporting it, but a smaller majority, less than 60% wanting it in those places. And so you can see that they do cluster a little bit, and some of our more tourism related communities are less supportive, and then the most supportive ones, if you know Michigan geography at all, tend to be places where there's maybe a bit higher unemployment. So that sets us up probably to understand a little bit better the next table, so if a person said they would support a biorefinery, we gave them a list of options of what's the biggest advantage of having a biorefinery in your area. If they said they would oppose it, we asked them what are the biggest drawbacks, and it was a list, a closed-ended list that we asked them to choose from. And so you can see that those who supported the biorefinery in their community, by far the biggest advantage was the job creation aspect of it, which makes a lot of sense if you think back to that map I just showed. That's, places where they're having trouble with jobs, they want those jobs in there. But there was another set that just felt it was good because it would reduce dependence on foreign oil. So that's a really interesting finding that they're thinking about that and wanting to have the facility in their area for those reasons. In terms of the opponents, the largest one was that they didn't think that biofuels were economically viable. So I'm imagining that would be an issue with that would be that they would be afraid that the facility would become a white elephant in their town, if subsidies were to go away, or maybe they're just simply opposed to some of the policies that Satish mentioned in his opening remarks. And then a second large group, 26%, were opposed because they thought it would be damaging to the environment in the long term. I was a bit surprised that so few people were concerned about the kind of the daily smells or noises or traffic kinds of issues, because we've heard a little bit about that from some folks, but apparently that wasn't a major concern from those who responded to the survey.
Okay, thank you, Scott. Okay, so I'll be talking about the optimal harvest shed design tool. As you know, there are many types of biomass. You could, for cellulosic ethanol production, you could use agricultural crop residues like corn stover, or you can have perennial grasses like miscanthus and switchgrass, and you can use woody biomass. And these feedstocks vary a lot in terms of how much is the yield per acre, what is the cost of production. Then depending on how much they produce yield, how much is the yield, the transportation costs vary, and the harvest windows vary. And plus, if you're interested in the greenhouse gas footprint, that also varies across different feedstocks. And also, there is a contracting issue, that is, nobody would like to grow switchgrass on annual contracts. You would want a long-term contract. And while agricultural residues like corn stover, probably you can afford to have annual contracts. So the idea is the refinery managers have to think about, okay, what length of contract and with what kind of feedstock, and where do I enter, and whether I should enter closer to the biorefinery or away from the biorefinery. And given that grasses produce different quantities or different times in their life cycle, so what's the temporal dimension of these contracts? So in order to do and help address this question, we have developed a fairly generic math programming model. So the idea is you visualize, in the math programming model, we visualize a biorefinery in the center. It is surrounded by concentric circular zones, let's say 5 miles radius, 10 mile radius, 15 mile radius, and so on and so forth, up to 50 miles radius. And the idea is to supply this biorefinery in the center with biomass from each of the concentric circles. So it's generic, and the idea is to minimize the total discounted cash costs of material, harvest, transport, storage, and plus externality costs like greenhouse gas emission costs over a 20-year period. And the idea is we'll make those decisions on a quarterly basis. So, and the decision variables are basically how much acreage of different feedstocks you enter into a contract each quarter and which zone. Okay, so the once you analyze that, the results will kind of tell you both the spatial distribution as well as the temporal distribution of your supply contracts. So, for example, a simple case study location, we did it analysis for a case in Kansas, and the results would somewhat look like this. Okay, so here is, for example, if you look at the this one, it tells you like you are going to the optimal, which minimizes the total biomass procurement cost, would be like perennial zone. So you will be, most of the perennial energy crops will be in zone 1 and zone 2, that is 5 to 10 mile radius, and most of it will be entering into contract in the first year, and a little bit to catch up volumes in between, and the 10th and 11th years, which basically that when you have to replant with a life of about 10 years. And agricultural residues, if you look at that, on this side will be entering into, most of this will be in zone, little bit in zone 3 and zone 2, and most of it is in zone 3 and zone 4, which are farther away from the biorefinery. And it looks like we'll be basically entering the basic production with energy crops, and the backfill will be done by agricultural residues. Okay. And if you, this is acreage, but if you're looking at the output, how much of feedstock will be used, you can see that most of it will be agriculture, energy crops in zone 1, and again in zone 2, which is 5 to 10 mile radius, it's all going to be agriculture residues with small quantity, excuse me, most of it is going to be energy crops with small quantities of agricultural residues, and most of the agricultural residues are coming from farther away zones. Okay, so that's kind of a example output from the model. So, I mean, even if based on this simple two feedstock model, we can kind of figure, we can kind of surmise that energy crops will likely account for a significant proportion of the optimal feedstock mix, though they have higher establishment costs, and you need to enter into long-term contracts. In our model for miscanthus, we'll be entering into a 10-year contract, and higher yields per acre and the associated lower transport cost offset probably whatever are the higher costs of feedstock production for energy crops, and agricultural residues likely to be used as primary to cover shortfalls in energy crops. And again, as you saw in the previous slide, most of these energy crops will be grown very close to the biorefinery rather than far. Okay, so that's kind of the basic, and now we have a more advanced model which has more feedstocks like wood chips and poplars in addition to miscanthus and switchgrass and agricultural residues. We also have an extension which covers multiple harvest sheds separated by water bodies, which is more applicable to the Great Lakes region. So water transport is cheaper, so sometimes it might be worthwhile for you to capture harvest from areas farther away on the other side of a lake. Okay, so these are those are kind of, that's the first tool that we talked about. And the next I'm going to do about how do we organize the supply chain. In that we are looking at key two alternative versions. One is the traditional one where you have a single biorefinery doing all the processing right in the center of the harvest shed, or what's called a distributed biomass pre-processing, in which you have a refinery and a number of this distributed pre-processing centers. We pre-process the biomass that's coming in, and the idea here is you can, it will hopefully it will reduce transport costs because you are going to pre-process it into to densify it, to chop it and pelletize it, and then that way it might reduce your transport costs. And by mixing it, you can have more uniform quality, more easy storage, and better transportation properties for the pre-processed biomass. And we are also interested in looking at whether if these pre-processing centers can produce alternative products like animal feeds or pellets for home heating or power plants, and that way, and if they end up being farmer owned or farmer cooperatives, then they can get a better share of the value chain. So that for all these reasons, we are interested in looking at the distributed pre-processing configuration, and we are specifically looking at what's called the AFX pretreatment, which is a process developed at MSU, and which is so the idea here is to pre-treat. I mean, there are a number of options for pre-treatment, and AFX is one of them, but AFX has a few specific advantages. That is, it converts biomass. Once you pre-treat, what makes it good for processing back in the biorefinery also makes it good for digestion in animals. And in fact, some studies at MSU show that the FX treated corn store is roughly equivalent to shelled corn in terms of energy and protein, and switchgrass is roughly equivalent to barley in terms of the nutrient thing. So the idea is FX treated biomass can be used as animal feed, so it creates an alternative market, and which also addresses the chicken and egg problem. That is, now that you can build your supply chain gradually, first producing either pellets or animal feeds, and then once the biorefinery comes up, you can start supplying it to the biorefinery. So you can gradually scale up. Okay, so I mean, if you just look basically without any just looking at the transport distances, it doesn't make sense to have it distributed, because you're going to have to transport once to the RBPC and then back to the biorefinery, and there will be double handling costs. So we have a simple spreadsheet model by which you can actually estimate how much of densification and what kind of distribution rural roads will help you make that simple transport cost estimates under different circumstances, and when it's economic purely on that. And then there are other advantages for the AFX pretreatment. That. So how do I assess the regional pre-processing facilities? Is it economically viable or not? So the idea here is we need to look at how much biomass is available and how do you estimate the cost, and then you need to estimate the capital and operating costs of what appropriately scaled RBPD or RBPC, and then whether there is enough market for animal feed, and whether it's the feed cost is competitive, and then which basically determines overall feasibility. So we have developed, with chemical engineers at MSU, developed some simple spreadsheet models for assessing the operating costs and capital costs of RBPCs at different scales. For example, here is an example. An RBPC with 25 tons per day capacity, the capital cost will be about $3.6 million, and operating costs to convert it into animal feed and biorefinery feedstock will be about $77 per ton. And compared to that, 200 tons per day capacity will cost about $15 million, but the operating costs will come down to about $34 per ton. So you can scale it up. So that spreadsheet model is available. And to use this, and the idea is, and we also developed some simple protocols for doing back of envelope feasibility analysis for different regions. So an example would be like we applied that to the eastern UP, which is the Bay Mills Indian community area. We are trying to assess whether RBPC will be feasible there. So the bottom line is it's not a financially attractive project. The cropland is relatively low at about 50 acres total availability. So even the max it can support is 150 to 200 tons per day capacity plant, and the capital costs are going to be $35 per ton, and there are not enough animals to, so there is not enough animal feed demand, so it's not a feasible option. So that's kind of the case study, but we could extend it to any other area. It's a fairly simple protocol by which you can do a back of envelope feasibility analysis. So now I'll kind of hand it over to Brent to talk about the next component, which is contract design research. Thank you.
So can everybody hear me okay? So I'm going to present two things. The first thing is some research we did looking at the design of contracts that producers would be willing to accept in order to sell biofeedstocks to the market or to the bioprocessor. And so in doing this, what we did was we conducted a series of focus groups and a follow-up questionnaire with 26 producers up in the eastern end of the Michigan Upper Peninsula in April of 2013. And so some of the key findings from that research were that producers were somewhat familiar with energy crops, and in particular with switchgrass, and also familiar with some other types of energy crops such as reed canary grass. But switchgrass was the one that they were most familiar with, as well as miscanthus. 87% of those producers indicated that they would commit roughly 21% of their land